Hello students, welcome back. Now let's go to section 4, some additional examples. As the title suggests, this is basically some miscellaneous topics that are not as important as the rest. However, do not completely disregard this part, especially if you are preparing for some kind of standardized test, such as Texas exam for high school teachers, or actuary exams, or things like those. Alright, let's begin with 4.1, binomial distribution. It's a review. We already studied it in section 3. Here's a probability mass function, and here is a cumulative distribution function. And also, here are the expected value and the standard deviation of binomial distribution, particularly for binomial sums. Okay, alright. Remember those. Now let's go to Poisson distribution. And Poisson distribution is a little special in a sense that it is a discrete random variable that takes infinitely many possible values. A k value can be any non-negative integer, 0, 1, 2, 3, 4, all the way over 2. Actually, not all the way over 2, just go on forever. So there are infinitely many possible values. All the discrete random variables we studied so far actually are finite random variables. Poisson distribution is a little bit different. By the way, this is the only infinite discrete random variable we have in our textbook, by the way. Is there anything else? No, I don't think so. I think this is the only one. Now, it's defined like this, and probability that x is taking a value k, where k is a non-negative integer, is like this, mu to the k power over k factorial times e to the negative mu power. And the student who already completed Calculus 2 will recognize that, mu to the k power over k factorial, this is coming from the coefficient of Taylor expansion of exponential function, and indeed we have an exponential here. So the student who completed Calculus 2 will see this. From Taylor expansion, sum of all the probabilities indeed is 1, but if you haven't taken Calc 2, then you don't know this. It's okay, I'm not going to stay too much on it. Now this one is cumulative distribution function because you see, you add it up to k not exceeding small x, so it's cumulative. Now the reason Poisson random variable is relatively important is because of this. It can be used as an approximation of binomial distribution. Binomial distribution is like this, n choose k, p to the k power, 1 minus p to the n minus k power, and this quantity can be what can I say, a really terrible computation for large n and k values. However, in a special case when probability p is very, very small and number of repetition n is very, very large, then you can use Poisson random variable so that this probability mass for binomial is approximately the same as this exponential expression, which corresponds to Poisson distribution. And the proof comes from this limit formula, but I don't know, it's a bit too much, so I'm not going to go there. Let's see. Is there a mathematical proof there? No, not really, just some mathematical computation. So it turns out like this, so we can use this as an approximation. And furthermore, the mean and variance happens to be the same. Same thing that goes up here, mu, and also there. Is there a proof? Well, there's a proof, and it requires calculus too, so there's going to be some Taylor series expansion involved here. And indeed, yeah, this is for expected value computation. Indeed, it's a Taylor series computation with some index shifting. Oh my goodness, so maybe it's beyond calculus 2. And what is this? This is for variance. Oh my goodness. If you can follow this, great, but if you can't, don't get mad at yourself. Don't get mad at me either, because I'm not requiring this. Okay, all right. Let's assume that we can use Poisson approximation for binomial if p is very small for our purpose and n is very large for our purpose, like this example. Okay, here we go. The Center for Disease Control and Prevention reported in 2012 that 1 in 88 American children had been diagnosed with autism spectrum disorder, ASD. Use Poisson approximation to answer the following questions. Okay, first question. If a random sample of 200 American children is selected, okay, n value is 200. That's large enough, I guess. And p is 1 in 88, so that's small enough. So what is the expected value and the standard deviation? Okay. Okay, what is the expected value? Out of 200, one in 88 student? As a matter of fact, this is not good. Let's rewrite like this. Okay, mu equals np, and that's part of the formula here. See? And then this is empirical values, so I use approximate values. So this quantity here you can calculate with your calculator. It turns out about like this. Okay, that's about right. Now, how about the probability standard deviation? Well, we have probability p, 188, and n value, 200. So can you find out the standard deviation? We have n value, we have p value. Can you find out sigma? Well, it is square root of n p 1 minus p for binomial sum, and that is 200 188 87 88. Is that clear to everybody? You see, n p 1 minus p. So let's calculate all these. Okay, so times that, times all that, and then calculate its numerical expression. 1.49 something, all right? Okay, so this is approximately like this. Okay, that completes part A of the problem. Any question? All right. I don't need these anymore. Everything is posted here anyway. Oh, by the way, here in the answer key, I have mu value, but I did not calculate the probability standard deviation. Okay. Now, what is the approximate probability that at least 2 children in a sample of 200 children have been diagnosed with ASD. So at least 2. So this is going to be probability that is going to be probability no student, no child, 1 child, 2 children. Is that clear? Okay. And then, so this is going to be 200 choose 0, 188 to the 0 power, 8788 to the 200 power. That's for no child. And then let's copy and paste this. For 1 child, 200 choose 1, and then 1 ASD. So 200 minus 1, so 199. And then for 2 children, second power, and this is going to be 198. Oh, by the way, this has to be approximate because all these are empirical figures. If you do that, and then you're going to get what you want. And oh boy, is this an easy computation? I don't know. For Mathematica, it may not be too bad. 200 choose k, all right, times 1 over 88 to the kth power, 87 over 88 to the 200 minus k power, and k going from 0 to 2, and let Mathematica calculate it, and this is what is sped out. That's because it calculated in terms of fraction precisely. So what about the decimal expression? It was quick. It was quick. So in today's computing power, is there any point for Poisson approximation? Is questionable, as a matter of fact. It could handle this binomial computation without too much trouble. But of course, about 50 years ago, it was still a difficulty with handheld calculator. 100 years ago, it was impossible computation. Poisson random variable, on the other hand, was much easier to handle. So we have something like this. Instead of this, we have, let's see. Yeah, this one. Mu to the k power, all right. What is the mu value here? Expected value was, yeah, this is the expected value, right? Excuse me, I already forgot what this is. Okay, all right. Let me copy and paste. So that's for 0 factorial, 0 factorial, and that's for 1 factorial and first power. And then this is for 2 factorial and second power. But then again, what is the mu value? Excuse me. No, not this one. This one. What is the mu value? Yeah, that was mu value we calculated before, n times p. And then so okay, we can calculate this. I thought I copied. I guess I didn't. Okay, what do we have? I have 0.90, and this is, oh, okay, this is first power, not second power. Okay, that makes a lot more sense. So this is what I obtained through Poisson approximation. And then, previous computation. Previous computation is here. Okay, let's compare. Previous computation and then Poisson approximation. This is directly from binomial, and this is from Poisson approximation. The difference is pretty small, isn't it? And then, of course, all these figures are approximate as well. So binomial does not have really strong motivation, as a matter of fact, because both are inaccurate figures anyway. So Poisson random variable, if it is more computationally effective, then it makes a lot of sense, even in today's purpose. But if you turn back the clock about 50, 60, 70 years ago, then this kind of computation was impossible. In that case, this was really way to go. Today, the motivation is not really there. But here's an approximation anyway. Let's see, what did I do in my notebook here? Yep, the same compute. Oh, the problem here is at least 2 children. So I should have calculated this one. What I did earlier was at most 2 children. That was the computation I did earlier. Well, it's not completely incorrect, so alright. I don't feel too bad. Here is solution for at least 2 children. So 0, 1, and then subtract from 1. And then previously what I did was at most 2 children. So 0, 1, 2, and then adding those up. Now what if you have a little bit bigger sample size and then fewer than 5? Directly from binomial computation was, oh my goodness, complicated. But even this wasn't too bad if you use Mathematica. In today's computing power, it's not too much of a deal. It just looks more intimidating if I write like this. From Poisson approximation, yeah, like this. So which is easier this time? Well, it's arguable. Many students will say in both cases binomial was easier, and it makes a lot of sense to tell the truth. And thus, Poisson random variable is getting less and less emphasis these days, I have to say. But still, if you're preparing yourself for some standardized test, who knows, it may show up, so do not completely throw that away. Otherwise, please consider this part as one of those optional topics. Okay, so much for Poisson, and we're going to talk about other examples in separate videos. Stay tuned.